Finally, in this video, I will present the proof of the fact that if Carnot-Carathéodory structures converge, then the associate distances converge uniformly on compact sets. There will be only one lemma left to prove, and I will prove it in the video after this one. So let's start. In this video, we prove the following theorem. Suppose you have f from a set of parameters times a manifold times Rm for some integer m into Tm, and n from lambda times m times Rm into R, such a way that this is a continuously varying CC bundle structure. See the previous video for this terminology. So this is one way of having time varying Carnot-Carathéodory structures depending on the parameter lambda. And let's assume that for some lambda 0 in lambda, the structure f lambda 0 m Rm, this is bracket generating. Then we're going to prove that the Carnot-Carathéodory distance associated to the structure associated to lambda converge to the lambda naught, as lambda converge to lambda naught uniformly on compact sets. Again, where this is the CC distance associated to f lambda m Rm and the norm n lambda. Okay, so we're going to prove it modulo the following theorem, following lemma, whose proof will be postponed to the video afterwards. This is the equicontinuity of the distance d lambda. So let me state it in two parts. So I will make it a little bit more precise than in the previous video. So on every compact set, so same assumption of the theorem, but for all k in M compact, and assume lambda also compact, that there exists, we need to fix a Riemannian distance for any Riemannian distance ρ. There exist alpha and beta homomorphisms of 0 plus infinity, such that alpha rho pq is less than distance p lambda pq less or equal than beta rho pq for all p and q in k. Okay. Actually, from the proof, we also have a second part, which I will also need to prove for the proof of the theorem, and this is the following: that for all radius r, if I look at the balls of center a given point, so fix a point P in M, of radius r with respect to the distance d lambda, and I take the union of all these balls, then this set does not get bigger and bigger, but it stays within a compact set. So exists K prime in M compact, such that we have this bound. So we have K prime. Okay, so let's start the proof of the theorem. So proof of the theorem modulo this lemma. So first part, let's prove that the distance associated to lambda 0 is less or equal than d lambda plus epsilon. Okay, so then what I need to prove is, so I fix some epsilon, I fix a compact set K, compact, and I need to prove this inequality for lambda close enough to lambda 0. So I also fix a Riemannian distance, fix rho Riemannian distance. So I get the alpha and beta from the lemma. Okay. So let's try to understand what is happening. So first of all, so we're going to take points P and Q in the compact set, and then we're going to join them with curves that are d lambda geodesic, or they're almost geodesic, and these curves they're going to have controls u lambda. But this is for the structure associated to lambda. What we will then consider are other curves. Let's call them, maybe I'll call them gamma. Gamma lambda with the 0, which is the curve with the same control u lambda, but for the structure lambda 0. And then what we will do, we will bound the lambda 0 distance, the lambda 0 distance, with the triangle inequality with this extra point. This will be very small, and then will be bounded using the crucial lemma, and then this length will be very close to this length in the respective structure. Okay, so first of all, let me make the observation about the d lambda distance of these 2 points. So if we take the d lambda distance, so let's make a note. For all points P and Q in K, and for all lambda and lambda, which, remember, we assume to be compact, then the distance d lambda PQ, this is less than beta of rho PQ, which is less than some fixed number, which is, we can take that to be the diameter respect to rho of K. Okay, which is a fixed number. So what you see is that the crucial lemma tells us that the d lambda distance on the compact set K has a uniform bound independent on lambda. This is going to be important. Okay, let's remember what is the distance, because we are going to realize the distance as the length of some curve, or almost. So recall that d lambda PQ, by definition, this is the infimum of the integral of curve of the length is lambda, okay, gamma t ut in dt, when u varies in L2 of 0, 1, 0, 1 valued in Rm. So where gamma is an absolutely continuous curve valued into m, such that, okay, gamma starts at P, ends at Q. Sometimes one put here gamma 1 equal to Q, but let me just write it as one of the conditions. and gamma dot at time t, this is equal to the structure f given fixed lambda along gamma with control ut. Okay, so let's call this system star. Okay, so gamma satisfies this number. Okay, so of course what we could okay, this is an infimum, may not be realized, but up to our error epsilon we can find a curve for which this integral, or a control for which the associated curve gamma realize this infimum up to an error epsilon. But now I would prefer to also reparameterize the control. Let me make a note about this. So the control U may be changed into some other control U tilde. In other words, gamma can be reparameterized in such a way that the integral of the norm of lambda gamma u, this is equal or is the same gamma u tilde associate gamma curve gamma and so it gives the same length, but now this function here is constant, and n lambda, maybe we should call it gamma sub u tilde, sub u tilde, u tilde is, of course, almost everywhere constant. Okay. In other words, what I'm restating is the fact that every curve can be reparameterized with constant speed. This is exactly the speed. Okay, so if we only consider controls that are of constant speed, then the consequence that we have is that for all epsilon, we already have, there exists u such that the distance between P and Q is equal to this constant lambda u plus epsilon. So not it's less or equal, where here this is constant, and we have the property star. I mean these three conditions. Okay, let's call this. Oh, this is, which means that this curve the curve gamma is almost adjacent. Okay, so we're going to fix later a curve with this property. Okay, but now I want to understand how I would like to discuss the support of curves that we are going to consider. Okay, and I would like to make this following calculation. So, okay, again, so for all lambda in capital lambda and for all pq in k, we fix some u in L2, and there for which we have gamma with this star, and delta lambda gamma u is less or equal this. Sorry, I just rewrote what I wrote in the previous. sorry, here I wrote it wrong. Yes, okay, sorry. So this should be almost an infimum. Okay, so let me move it around. So this number here should be less, should be almost realizing the minimum. Okay, sorry. Okay. So this is what means that this number here almost realized the minimum. As soon as I add some epsilon, I can find something smaller. Okay, sorry. Okay, let's rewrite. So it was, okay, in fact, here I wrote it correct. Okay, now what happens? So a consideration on the support of gamma. So the d lambda distance between p and gamma at some time t, this is, of course, is less or equal than the integral between 0 and t of n lambda gamma u, say in ds. And this is less or equal than the integral between 0 and 1 and lambda gamma u. And this is less or equal than d lambda d lambda p q, which is less or equal than beta, because now pq are in the compact set, is beta than rho of pq, which again is plus epsilon here, plus epsilon, and this is less or equal than p, the diameter with respect to rho of k plus epsilon. So now what we've checked is that all these distances are uniformly bounded, independent on lambda. And therefore, gamma, what we have is that gamma t is in the ball respect to distance d lambda, center of p, radius r, where r is the radius which we define here. Okay, but we know from the assumption of, from the conclusion of the crucial lemma is that the union of all these balls are within a compact set. Exist such a compact set. Okay, so what do we have in conclusion? We have that all the curves that we are considering stay within a compact set k prime, which for simplicity you can think of to be equal to k, but actually maybe it should be considered bigger. Okay, so up to this point we haven't chose any small neighbor of lambda naught. We just made considerations of curves that we were considering. Okay, and what we also have is that if lambda is in the set of parameter, which is compact, and x is a point in k prime, then what we have, we are considering norms that are smaller than beta, this diameter, I mean this is r, diameter of k, plus epsilon. So you see, we said that we can consider this object is constant, no? Right? So this is bounded uniformly by this number here. So we have realized that gamma is within a compact set. And now what about u? Because this function is a norm, so fixed gamma, this is a norm, it's also continuously changing in gamma and lambda, then what we can say is that the set on which u lives is also a compact set. Okay, I call it V, right? So if V is such that we have this inequality, then V is within a compact set, let's call it K double prime in Rm. Okay, so to write it better, I should say there exists a compact set K prime such that if for lambda in capital lambda, x in K prime, V is a point with this, is a vector with this bound, then V is in the set K double prime. Okay? So now we have three compact sets. We have K, the initial set of the manifold. We have K prime, an enlargement. And then we have this K double prime is a set of vectors in Rm. Okay? Now we are going to choose some parameters and finally choose a neighborhood of lambda naught. So remember, so we have K in M compact, and now we are going to look at the vector fields F lambda V. Okay, now by assumption, what we have is that, remember, F is giving vector fields that are equi-Lipschitz. This is one of the assumptions on the continuously varying CC structures. Okay, so this implies that there exists L such that for all lambda in this compact set lambda, and for all V in this compact set K double prime, this vector field is, the vector field is L Lipschitz on K, so where this entry is in K. Okay, so we have this parameter fixed L, and now because of continuity of the subRiemannian, the CC structure, what we can choose some delta such that for all lambda in the ball in the space of parameter lambda around lambda 0 radius delta, we have that for all x in the compact set K prime and for all V in the compact set K double prime, we have that for all other points y that are in the respect to the metric rho at distance at most delta from x, we have continuity. So we have the first property. It's going to be n lambda 0 x v minus n lambda y v is less than epsilon. Okay, so this is just the continuity of n in these two variables, right? So uniform on compact sets. Okay, so we choose this delta in this way. Now, what we will do, we will choose A, set A, the number such that A, so this is because we are going to use Cromwell. This is less than delta, this first delta. And then we choose a delta, one more delta, smaller. So let's say that, so we are going to choose now another delta. So the first one is delta 1 and the second one is delta 2, such that we still have the first property for delta 1 and delta 2, for delta 1, but then we also have that the bundle map lambda 0 f lambda 0 x v minus f lambda x v is less than A. Okay, so and this is, so of course we can take lambda 2 smaller than that lambda 1, and this is up to shrinking the possible lambda. Here we can assume that you also have the second property. Okay, so now we have chosen the neighborhood of lambda for which we are going to have the distances are going to be close to each other. So we are ready to bound distance d lambda 0. Okay, so now take points P, Q, and K, then take lambda in this neighborhood we choose. Okay, now for these points P and Q, we can take U lambda, a control, with a star, which is a star of lambda. Where is it? With this equality when here is, with this system when here there is this lambda. Okay, so we choose such a control, which also almost realized the distance. Okay, U lambda, so equal in this d lambda pq plus epsilon, where I mean that this is, again, this is almost everywhere constant, and this curve is the curve associated to U alpha. Okay, now what we are going to do, we consider the curve gamma lambda 0, let's call it gamma, the solution of the system, okay, start at the same point, P, but the derivative is, so if I just write this system, this system would just give me the curve gamma lambda. So this is the control that gives me this curve, which almost realized this. But now I'm going to write here lambda 0. So this is a different, possibly different system of ODE. So, and I consider this curve, and then I set Q bar to be the final point of this curve. Okay, picture. Again, I draw it before. So I have P and I have Q in the compact set. Then I join them with gamma lambda, which is d lambda almost geodesic with control u lambda. Of course, this is with respect to f lambda and constant norm or constant speed. And then what we do, we consider the curve that starts at the same point, gamma lambda 0, and its final point is going to be q bar. And this curve here is a curve with control u lambda, same control, but this is with respect to f lambda 0. F lambda 0. Okay, so what we are going to bound soon is the distance, the lambda in P and Q. This is, of course, is the distance, is less or equal than the distance from P to Q bar plus the distance from Q bar to Q. Okay, now, how do we bound these two terms? Okay, now, first of all, how much Q bar differ from Q? So I would like to say that these are very close to each other. So we ask ourselves how much Q bar, which is gamma of 1, 0, I don't know, was lambda 0 at 1 differs from P. Actually, a slightly more general question: how much the curve at time t differs from the initial curve at time t? And now that's when we are going to use Gromwall. So gamma lambda is the integral curve of the time-dependent vector field f lambda u lambda t. And instead, gamma lambda 0 is the integral curve of f lambda 0 u lambda t. And also they have the same initial points. Now, let's check that the assumption on Gromwall lemma are satisfied. Okay, so we have to check that this first vector field u lambda t at time t, and the other vector field at a possibly different point, but at the same time, has the coarsely Lipschitz bound. And how we do it? Okay, triangle inequality. This is less than f lambda x u lambda t minus f. Let's put with the same point first. F lambda 0 x u lambda minus f lambda 0 y u lambda. Okay, so I added and subtracted this, and then I use triangle inequality. Okay, now for the first bound, this one, what we know is for how we chose delta, this is less than a. Let's see what we have. We have the same controls. We stay in this compact set K double prime, and points that are inside the set K double prime, K prime, and therefore we have the bound, this one here, x is in K prime, v is in K double prime, and then since lambda and lambda 0 different by delta, we have this first bound. Okay. So here we used 2, okay? So we use equation 2. And then in the second one, instead, we're just going to use the fact that we have a Lipschitz. F is a Lipschitz vector field, right? It was uniformly, we have this L that was uniform in X, in lambda, okay? Good. So we satisfied the Gromwall Gromwall condition. So Gromwall implies that the Riemannian distance between gamma lambda t, gamma lambda t, this is less or equal a e l t minus 1 divided by L, which for how we chose A, this is less or equal than delta. So, for example, so what we have understood is that the distance between Q and Q bar is less than delta. So let's call this inequality G. So we have this Gromwall inequality. We're going to use it. Okay. Remember what we want to bound. We have d lambda pq is less than d lambda 0. D lambda 0 p q bar plus d lambda 0 q bar q. So now the first part, the first term. So d lambda 0 p q bar, this is the infimum of curves connecting p and q bar respect to the structure n lambda, where the length is n of lambda 0, and now I can choose the control u lambda, and the associate curve was gamma lambda 0. So t in dt, right? So this curve is exactly a curve. This curve connects P to Q bar. By definition of Q bar is the endpoint of this curve. So, and this distance therefore is less than this length. Now, because of Gromwall inequality, we know that this point is close to the point gamma lambda t by an amount less than delta. And because of the first condition on delta, we have the norm when I change lambda and the point differs by at most epsilon. This was the first condition. Let's find again the first condition. Now we have that since these 2 points differ by delta and this point differ by delta, the norms differ by epsilon. Okay, I've used this fact. Okay, so we have this bound, and now because of how we chose the control u lambda, we have that this is less than equal than d lambda pq plus 1 more epsilon, so they become 2 epsilon. So this bound here, this term here has been bounded in the way we like it, so with the distance between the same points, now distance d lambda, plus an error in epsilon. Okay, so let's finish with the second term. So second, d lambda 0 of q bar q, this is less than equal. Now let's use the crucial lemma. So this is the points stay in the same compact set. So it's beta of rho of q bar q and as you said, this is less than this number, because of Gromwall, was less than delta, which is also less than epsilon, if you want. So this was less than beta k epsilon. And what's important is that this goes to 0 as epsilon goes to 0. So in total, what we have that the d lambda 0 pq is less or equal than d lambda pq plus 2 epsilon plus beta of epsilon, which this is a term that goes to 0, and therefore one bound is done. Okay, I will now quickly discuss the second bound, but the proof is exactly the same. Maybe it's a little bit even easier. 2. So d lambda less or equal than d lambda 0 plus epsilon. How do you do this? So this is a similar argument. Maybe even easier. So again, as before, we fix epsilon, we fix compact set k, and Riemannian distance rho. We get alpha and beta from lemma. Then what we do, we choose delta as above, as before, and we get the two conditions plus the Gromwall estimate. So this is norms are close to each other, and this is vector fields are close. And then what we do, we bound for all p and q in k. We take, now the control will not depend on lambda, because this is a control for the limiting this structure. So this is an almost a geodesic, in the sense that d0 pq I should put first that n lambda 0 gamma u is less or equal than d0 plus epsilon, and again we can assume that this is almost everywhere constant. And what we do, we take now the curve gamma lambda to be the integral curve of the time-dependent vector field f lambda u. And this is the control of the first curve gamma. And starting at the same point. Starting at P. Again, as before, Q bar is going to be the endpoint of this curve. And then we do exactly the same bound. Then d lambda PQ is less or equal than d lambda PQ bar plus d lambda Q bar Q. Now, the first one is less than the candidate curve gamma, and the second one is just by equicontinuity, beta rho of Q bar Q. The first one, now we use Gromwall plus the bound on the norm is lambda 0, gamma lambda u. And the second is just beta epsilon. So from here we have Gromwall, and here we use Gromwall plus the first bound. The second bound was obtained to get to Gromwall, and then this is less or equal than the, so this was, okay, plus epsilon, I should add here plus epsilon. And now this is d lambda 0 pq plus 2 epsilon plus beta epsilon. And this is the proof of the theorem. Done. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel, clicking below.